Before you journey deeper into the cosmos with us, if you're captivated by the mysteries of the universe and wish to explore more profound questions about existence, time, and creation like this video, and subscribe to our channel. Turn on notifications so you never miss our expeditions into the deepest mysteries of science and philosophy. Your curiosity is the fuel that propels us forward into the infinite. Beneath velvet cosmic silence lies a question that has haunted humanity since the first eyes gazed upward into the night. Where do galaxies begin? In what distant epoch, shrouded by time's relentless march, did the first lights ignite? The universe we observe today, this magnificent tapestry of billions of spiraling islands, each containing hundreds of billions of stars, emerged from a realm almost incomprehensible to the human mind. Shadowed by impenetrable darkness, the early cosmos was a sea without shores, unformed and seemingly endless, waiting for forces to breathe and structure into its depths. Before any sun burned or star shimmered, primordial forces drifted through space-time itself, entangling in quantum uncertainty. This was an era of raw potential, distant and seemingly barren, yet teeming with the seeds of everything we see. Galaxies are not merely collections of stars, gas, and dust scattered randomly through the void. They are ancient ships drifting through infinite night, woven by mysterious energies we are only beginning to comprehend. Their birth is neither sudden nor simple, but an unfolding tapestry woven from chaos and grace, shaped by gravity's invisible hand and sculpted by the rules of physics itself. What power carved these spiraling cities of light from the cosmic quiet? What mystery gave rise to their infinite forms? And as we peer back into the abyss, our curiosity echoes through the darkness. Are we witnessing the universe remembering its own genesis? The quest to understand galaxy formation is not merely a scientific endeavor. It is a profound meditation on creation and fate, on how infinite worlds emerge from nothingness. Tonight, the cosmos whispers its secret, and we drift closer to the answer. The story of galaxy birth begins not with cosmic observation, but with human wonder. It begins with those who dared to question the nature of the faint smudges of light that had dotted the night sky since time immemorial. For centuries, astronomers gazed upon these nebulae, the cloudy stars, as ancient philosophers called them, and debated their true nature. Were they nearby clouds of gas? Or something far more distant and profound? The answer came not all at once, but through the patient, meticulous work of one man who transformed our understanding of the universe itself. In the early 1920s, Edwin Hubble, perched atop Mount Wilson in California, directed the most powerful telescope on Earth toward these mysterious objects. Using a technique called spectroscopic parallax, he measured the distance to Cepheid variable stars within what was then called the Andromeda Nebula. The results stunned the astronomical community. These were not nearby gas clouds, but distant galaxies, islands of stars, comparable in scale to our own Milky Way, positioned far beyond the edges of our galactic home. This discovery fundamentally rewrote humanity's place in the cosmos. The universe, once thought to be contained within our singular galaxy, suddenly expanded exponentially. Where once there had been one island, there were now revealed to be billions. The expansion did not stop with distance. It extended into time. Hubble's subsequent observations revealed that distant galaxies exhibited redshifts. Their light stretched toward longer wavelengths, indicating that the universe itself was expanding, stretching like an elastic fabric woven through the void. But the question of origins remained unanswered. If galaxies were scattered throughout space, receding from one another in all directions, how had they come to be? What forces had gathered the primordial gas into these magnificent structures? The first real clues emerged not from individual galaxies, but from deep surveys of the entire cosmic landscape. The Hubble Deep Field, observed in December 1995, became a turning point in modern astronomy. Scientists directed the Hubble Space Telescope toward an apparently empty region of sky no larger than a grain of sand held at arm's length. What emerged from that patch of darkness was revelatory. Thousands upon thousands of galaxies, each a separate system of stars, stretching back to the very dawn of cosmic time. These were not nearby structures but ancient artifacts, their light having traveled for billions of years to reach Earth. Each image was a window into a different epoch of the universe's history, a frozen moment from cosmic adolescence. In those images lay the seeds of a deeper mystery. The galaxies revealed in that small patch of sky showed an astonishing diversity. Some were disc-shaped, their arms wreathed in blue light from young stars. Others were elliptical, vast and ancient, glowing with the amber warmth of stellar populations, billions of years old. Still others were irregular, twisted into strange geometries as if they had been violently disturbed or caught in cosmic collisions. Behind these observations stood legions of astronomers, armed with telescopes in remote mountains and deserts. In Chile's Atacama region, atop Mauna Kea in Hawaii, and in space itself, humans assembled arrays of mirrors, detectors, and spectrographs. Each instrument was designed with a singular purpose: to pierce the cosmic veil and glimpse the epochs when galaxies first formed. Radio astronomers detected emissions from hydrogen gas, the most abundant element in the universe, tracing back to the universe's youth. Infrared instruments revealed dust-shrouded galaxies that visible light could not penetrate. The quest was not merely technological, it was fundamentally philosophical. At its core lay an existential yearning to know what lay beyond the horizon of our knowledge. The early discoveries hinted at a cosmos far more complex and ancient than previous theories had suggested. Each observation raised new questions. Each breakthrough opened new mysteries. The story of galaxy formation was beginning to unfold, not as a simple narrative, but as a labyrinth of wonder and paradox. Yet, as observations accumulated and data multiplied, the scientific community faced a growing crisis of comprehension. The galaxies revealed by telescopes seemed to violate the very laws of physics that had guided cosmological thinking for decades. Theories that had predicted how galaxies should form and evolve began to crack under the weight of observational reality. The first shock came from an unexpected direction: galactic rotation. When astronomers measured how quickly galaxies spun, tracking the motion of stars and gas clouds at their edges, numbers defied explanation. According to classical mechanics and gravitational theory, stars at the outer regions of galaxies should move more slowly than those closer to the galactic center, much as planets farther from the Sun move in slower orbits. The observations, however, revealed something startling. Outer stars moved at nearly the same speed as inner stars. This was physically impossible unless vast quantities of invisible matter, present but undetected, provided additional gravitational force. This was the revelation of dark matter, made famous by the pioneering observations of astronomer Vera Rubin in the 1970 seconds and 1980 seconds. She demonstrated that galaxies must contain 5 times more mass in invisible material than in stars and gas. This invisible substance, later called dark matter, was terrifying in its implication. The universe was not as we saw it. What humanity perceived as the cosmos, all the stars, planets, and glowing gas constituted less than 20% of all matter. The rest was shadow, a cosmic phantom whose nature remained profoundly mysterious. But the shock extended beyond the invisible. Recent observations from the James Webb Space Telescope revealed galaxies that shouldn't exist. Deep in time, mere hundreds of millions of years after the Big Bang, astronomers discovered massive galaxies, structures that should have required billions of years to assemble through gravitational processes. These red monsters, as researchers called them, appeared impossibly mature. Their cores dense with billions of stars, their stellar populations ancient and metal-rich, existing in an epoch when the universe should still have been young and primitive. This discovery struck at the heart of cosmological timelines. If galaxies could grow to such enormous scale so quickly, the mechanisms driving galaxy formation must be far more efficient than theories suggested. Perhaps galaxy mergers occurred more frequently, combining smaller systems into larger ones with remarkable speed. Perhaps the first generation of stars, formed from primordial hydrogen and helium alone, generated elements through nucleosynthesis and then exploded as supernovae, seeding new regions for rapid star formation. Or perhaps something more exotic was at work, physics beyond the standard models that governed cosmic evolution. The shock deepened with each new discovery. Some galaxies exhibited peculiar chemical compositions, with more heavy elements than could be explained by stellar nucleosynthesis alone. Others displayed unusual morphologies, their spiral arms asymmetrical or their cores displaced from their geometric centers, suggesting gravitational disturbances or collisions. Some showed signs of extreme star formation, with young blue stars appearing where elderly red stars should dominate. The cosmic gallery revealed not a universe of orderly progression, but one of turbulence and unpredictability. Supernova explosions, once thought to be localized events, revealed themselves to be cosmic dynamos, capable of expelling enormous quantities of gas from galaxies, creating vast galactic winds. These outflows would strip young galaxies of the fuel necessary for future star formation, fundamentally altering their evolutionary trajectories. Yet this same feedback mechanism appeared necessary to explain why galaxies didn't become even more massive than observations revealed, as if the universe possessed a built-in throttle on cosmic creation. Most unsettling was the realization that the theoretical frameworks governing astrophysics, general relativity, quantum mechanics, and classical hydrodynamics seemed insufficient to explain the full diversity of observed phenomena. The universe at the epoch of galaxy formation was not the serene, mathematically precise cosmos that 20th century physics had described. It was turbulent, complex, and populated by forces that science was only beginning to comprehend. The scientific shock was not temporary confusion to be resolved by minor adjustments to existing theory. It was a fundamental crack in the edifice of cosmic understanding, a reminder that reality often exceeds human expectation, and that the universe remains profoundly mysterious in ways we have barely begun to fathom. Confronted by these paradoxes, the scientific community mobilized with renewed urgency. If galaxies formed in ways that defied conventional understanding, then understanding their birth required new tools, new data, and new frameworks of interpretation. The investigation deepened, probing ever further into cosmic history and structure. Cosmologists turned their attention to the cosmic microwave background the ancient light released when the universe was merely 380,000 years old. After electrons combined with nuclei to form the first atoms, this radiation, discovered accidentally in 1964, carried within it the imprints of the universe's earliest moments. The Planck satellite, launched in 2009, mapped this radiation with unprecedented precision, revealing tiny temperature fluctuations, ripples in the cosmic fabric, representing regions of slightly higher and lower density. These density variations were the seeds from which galaxies would eventually grow. Where the early universe was slightly denser, gravity would pull more material inward, initiating a cascade of gravitational collapse. Where it was slightly less dense, regions would remain comparatively empty. The pattern of these cosmic seeds, mapped in the microwave background, held the key to understanding how the first galaxies formed and why they possessed the properties astronomers now observed. Yet mapping seeds was only the beginning. Scientists needed to trace the process by which quantum fluctuations became protogalactic clouds, and protogalactic clouds became the galaxies we observe today. The investigation required multiple approaches, each illuminating different aspects of the cosmic story. Spectroscopic analysis revealed the chemical fingerprints of ancient galaxies, allowing astronomers to trace the history of element creation. In the early universe, only hydrogen and helium existed, the products of Big Bang nucleosynthesis. Every heavier element, carbon, nitrogen, oxygen, iron, and all the rest, had to be created in the cores of stars through nuclear fusion and dispersed into space through supernova explosions. By measuring the abundance of heavy elements in ancient galaxies, scientists could infer how many stellar generations had already lived and died, providing a census of cosmic history. The investigation revealed another profound mystery. Ancient globular clusters. These tight, ancient assemblies of hundreds of thousands of stars appeared to be among the oldest objects in the universe, with ages approaching the age of the universe itself. Some existed within galaxies, while others orbited the galactic periphery like cosmic relics. Their ancient light contained no heavy elements, only the primordial hydrogen and helium from the Big Bang. This suggested that globular clusters might represent the first generations of stars to form after the cosmic dark ages, the vanguard of the epoch of reionization, when the first stars and galaxies ionized the neutral hydrogen pervading the universe. The cosmic web, the large-scale structure of the universe, became another avenue of investigation. Galaxies were not randomly scattered through space, but arranged along filaments of dark matter, like cities along roads, invisible to the eye. These filaments formed a vast network spanning billions of light years, with galaxies streaming along their paths, merging and evolving under gravity's influence. Mapping this structure required cataloging millions of galaxies, measuring their distances and velocities. The Sloan Digital Sky Survey, one of the most ambitious astronomical projects in history, did precisely this, creating three-dimensional maps of the cosmos and revealing the intricate skeleton upon which all visible structure hung. At galactic centers, investigations revealed the presence of supermassive black holes, objects of such extreme density that space-time itself became distorted beyond recognition. These cosmic leviathans, millions or billions of times more massive than the Sun, appeared to exist in nearly every galaxy. Their role in galaxy formation remained enigmatic. Did they seed the earliest galaxies, or were they formed later as smaller black holes merged? And what was the relationship between black hole mass and galactic properties? These questions drove deeper investigation. The interstellar medium, the gas, dust, and radiation filling the spaces between stars, revealed itself through infrared and radio observations to be far more dynamic and complex than previous understanding suggested. Supernova explosions created expanding shells of hot gas. Stellar radiation carved out expanding bubbles. Molecular clouds collapsed under gravity to form new stars. The universe within galaxies was not a vacuum, but a turbulent ecosystem where creation and destruction danced in perpetual struggle. Each investigation opened new pathways of understanding while simultaneously revealing deeper layers of mystery. The investigation was not a linear march towards certainty, but a spiral descending into greater complexity and profundity. As investigation proceeded, the mystery did not diminish but intensified, revealing dimensions of cosmic complexity that challenged the foundations of physical understanding. The escalation was not gradual but precipitous, with each new discovery suggesting that the universe operated according to principles far stranger than theoretical frameworks predicted. The escalation began with the observation of cosmic acceleration. In the late 1990 seconds, observations of distant supernovae revealed that the expansion of the universe was not slowing under gravity's attraction, but accelerating. Some form of energy distributed throughout all of space was driving galaxies apart at ever-increasing speeds. This was the discovery of dark energy, a component of the universe constituting approximately 68% of all energy density. What dark energy was remained profoundly mysterious. Was it Einstein's cosmological constant, a property of space-time itself? Was it something more exotic, a quantum field permeating all existence? The implications were staggering. 3/4 of the universe was composed of two substances, dark matter and dark energy, about which science knew almost nothing. In this accelerating cosmos, galaxies faced an escalating challenge. As the universe expanded faster and faster, the gravitational pull holding matter together grew relatively weaker. Galaxies within a certain distance would eventually separate so far that their mutual gravity could never reunite them. The window for galactic mergers and interactions was closing. Yet, observations revealed that massive galaxies continued to form and grow, colliding and combining with remarkable regularity throughout cosmic history. How could galaxies achieve such growth in a universe actively working against gravitational assembly? The answer lay in the violent processes occurring within galaxies themselves. At the cores of galaxies lurked supermassive black holes, cosmic engines of incomprehensible power. As material orbited these objects, spinning inward in accretion disks, gravitational forces heated the material to billions of degrees. Tremendous jets of radiation and particles erupted from the black hole's poles, traveling outward at nearly the speed of light. These jets, extending for millions of light years, possessed enough energy to heat or expel entire galaxies' worth of gas, fundamentally reshaping galactic evolution. The phenomenon of active galactic nuclei galaxies, powered by accreting supermassive black holes, revealed that galaxy formation was not driven by gravity alone. Feedback mechanisms, both radiative and mechanical, appeared to be essential regulators of cosmic structure. The very forces driving star formation also appeared to limit it, preventing galaxies from becoming infinitely massive. The universe seemed to possess a built-in mechanism for cosmic birth control. Yet the escalation of mystery extended beyond the interactions within individual galaxies. Galaxy clusters, vast assemblies of hundreds or thousands of galaxies bound together by mutual gravity, revealed themselves to be even more complex than single galaxies. The most massive clusters produced conditions of such extreme density and temperature that they generated the hottest matter in the universe, gases hundreds of millions of degrees in temperature. These were cosmic furnaces where elements were synthesized, where physics was pushed to extremes, where the classical laws of gravity and thermodynamics occasionally seemed to bend and twist. The hierarchical nature of cosmic structure created a cascade of mysteries. Smaller structures merged to form larger ones. Galaxies merged to form elliptical giants. Galaxy groups merged to form clusters. Clusters aligned along filaments to form superclusters. But the efficiency of merging appeared to exceed theoretical predictions. Simulations suggested that mergers should occur less frequently than observations revealed. Something was missing from the physical models, some aspect of cosmic dynamics that simulations failed to capture. Further escalation came from the observation of cosmic reionization. In the earliest epochs of the universe, a few 100 million years after the Big Bang, space was filled with neutral hydrogen, opaque to light. Then, suddenly, the first stars and galaxies ignited. Their ultraviolet radiation, capable of ionizing hydrogen atoms, began to spread through the cosmos like a wave of enlightenment penetrating darkness. Gradually, the universe transformed from a neutral, opaque state to an ionized, transparent one. Yet, the process appeared to occur more rapidly and completely than theoretical models predicted. What drove such efficient reionization? Which galaxies were responsible? The questions multiplied. At the deepest levels of investigation, an unsettling realization emerged. The universe appeared to be more creative, more dynamic, and more bizarre than human imagination had conceived. Dark matter formed an invisible scaffolding upon which visible structure hung. Dark energy pushed everything apart. Quantum fluctuations from the Big Bang's earliest moments had somehow crystallized into a universe of almost infinite complexity. The forces driving galaxy formation, gravity, stellar feedback, black hole feedback, radiation pressure, supernova explosions interacted in ways so intricate that even supercomputers struggled to simulate them accurately. The mystery deepened into existential uncertainty. If galaxies formed through processes so complex, so dependent on the precise interplay of countless factors, was galaxy formation inevitable? Could the universe have evolved differently, producing no galaxies at all? Or was there something in the fabric of reality, something fundamental about the laws of physics that made the emergence of galaxies and stars essentially inescapable? Most disturbingly, observations suggested that our theoretical understanding of physics itself might be incomplete. The standard model of particle physics, the theory of general relativity, the framework of quantum mechanics, the entire scientific edifice constructed over the past century, appeared insufficient to explain the full complexity of galaxy formation. Unknown particles, unknown forces, or unknown principles might yet be waiting in the cosmos, hidden within the most ancient light and the most distant galaxies. The escalation was not toward resolution, but toward recognition of profound cosmic ignorance. The deeper science ventured into the mystery of galaxy formation. The stranger and more wonderful the universe revealed itself to be. In the face of these cascading mysteries, the scientific community constructed frameworks of understanding theories, both grounded in rigorous observation and extended through speculative but credible interpretation. The most comprehensive of these frameworks became known as the lambda-cold dark matter model, the LCDM concordance cosmology. This model synthesized decades of observations and theoretical insights into a coherent narrative of cosmic evolution. At the foundation of the LCDM model lay Einstein's general theory of relativity, the most profound and accurate description of gravity yet conceived by human minds. According to Einstein, gravity was not a force in the Newtonian sense, but the curvature of spacetime itself, caused by the presence of mass and energy. In the earliest moments after the Big Bang, the universe was infinitely hot and dense, infinitely curved. As it expanded, it cooled, and the curvature became less extreme. The geometry of spacetime itself became the stage upon which cosmic evolution played out. Yet Einstein's general relativity alone could not explain observations. The universe possessed far more mass than visible matter, hence the dark matter component, comprising 85% of all matter in existence. Dark matter particles, whatever their nature, contributed to spacetime curvature without emitting light. They provided the gravitational scaffolding upon which galaxies formed. Scientists proposed candidates: WIMPs, weakly interacting; massive particles; axions; sterile neutrinos; exotic particles predicted by extensions to the standard model of particle physics, yet never definitively detected. The dark energy component, comprising 68% of all energy density, remained even more mysterious. The prevailing interpretation was that dark energy represented a property of spacetime, itself what Einstein had called the cosmological constant. According to quantum field theory, empty space was not truly empty, but seething with virtual particles and fields. This quantum vacuum possessed an inherent energy density, a kind of negative pressure that pushed matter apart. Yet the magnitude of this effect was problematic. Quantum theory predicted a vacuum energy, many orders of magnitude larger than observations revealed, a discrepancy known as the cosmological constant problem, one of the deepest unsolved problems in theoretical physics. Alternative theories ventured into speculation. Phantom dark energy, a form of dark energy violating classical assumptions, could lead to a big rip, where the accelerating expansion would eventually tear apart even atoms. Modified gravity theories, such as MOND, modified Newtonian dynamics, proposed that gravity itself behaved differently at cosmic scales, eliminating the need for dark matter while maintaining consistency with observations. Multiverse theories suggested that the universe we observed was merely one of countless universes, each with its own physical constants and properties. The theory of cosmic inflation, developed in the 1980 seconds by Alan Guth, André Linde, and others, provided a crucial mechanism for understanding cosmic origins. According to inflation theory, in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. Quantum fluctuations occurring during this inflationary epoch were stretched to cosmic scales, becoming the seeds of all future structure. Inflation explained why the universe appeared so homogeneous on large scales. Inflation had stretched a tiny, uniform region to cosmic proportions, while also explaining why small variations in density existed. Quantum fluctuations were the source of these variations. The theory of stellar nucleosynthesis described how elements were created. In the cores of stars, nuclear fusion converted lighter elements into heavier ones, generating the heat and light that made stars shine. When massive stars exhausted their nuclear fuel, they collapsed catastrophically and then exploded as supernovae. dispersing newly created elements into surrounding space. These elements, incorporated into new clouds of gas, became the raw material for new generations of stars. Each stellar generation produced more heavy elements, gradually enriching the cosmic material from which later stars formed. Hierarchical assembly theory provided a framework for understanding galaxy formation and evolution. According to this theory, the smallest structures formed first dwarf galaxies, and protogalactic clouds assembled from dark matter halos of limited mass. These small systems then merged under gravity's influence, combining into larger and larger structures. Through a cascade of mergers spanning cosmic time, small systems evolved into giant elliptical galaxies. Spiral galaxies, by contrast, formed through more gentle, secular evolution. Gradual processes of star formation and gravitational processes within existing structures. The Gunn-Peterson effect and Lyman alpha forest observations provided evidence for cosmic reionization. As the first galaxies formed and stars ignited, their ultraviolet radiation propagated outward, ionizing neutral hydrogen. The Lyman alpha forest absorption lines visible in the spectra of distant quasars trace neutral hydrogen, persisting in the intergalactic medium, revealing how reionization proceeded in a patchy, uneven manner, with ionized bubbles expanding around the first galaxies and eventually merging to reionize all of space. Feedback mechanisms emerged as central to galaxy formation theory. Supernovae explosions from massive young stars heated gas and drove outflows from galaxies, limiting star formation. Radiation pressure from young stars pushed gas outward. Radiation from active galactic nuclei heated surrounding gas, preventing it from cooling and accreting onto black holes. These feedback processes, incorporated into sophisticated computer simulations, allowed models to reproduce the observed population of galaxies with reasonable fidelity. Yet all these theories, grounded in real physics and constrained by real observations, extended into speculative territory at the frontiers of knowledge. What was dark matter really? What was dark energy? Were there additional spatial dimensions? Did quantum mechanics or general relativity require modification at extreme scales? Could exotic physics, false vacuum decay, quantum tunneling to alternate vacuum states, or unknown phenomena drive aspects of galaxy formation? The theories represented humanity's current best understanding of cosmic genesis, a framework within which to organize observations and ask new questions. Yet they were not final truths, but provisional maps of a territory still largely unexplored. Each theory contained unresolved tensions. Each pointed toward mysteries yet to be unraveled. The act of theorizing was not an assertion of knowledge, but an acknowledgement of ignorance, an attempt to bound the unknown and identify where future investigation must focus. The quest to understand galaxy formation proceeded not merely through theoretical speculation, but through relentless empirical investigation, using the most sophisticated instruments ever constructed by human hands. These tools, pushed to the limits of technological capability, transformed understanding by providing unprecedented windows into cosmic history. The Hubble Space Telescope, launched in 1990, revolutionized observational astronomy. Freed from the distorting effects of Earth's atmosphere, Hubble could observe distant galaxies with clarity impossible from the ground. Its observations of Cepheid variables in nearby galaxies refined cosmic distance measurements. Its deep field images revealed the universe's true complexity. Its spectroscopic capabilities allowed measurement of galaxy redshifts, providing information about their distances and velocities. For more than 3 decades, Hubble remained the gold standard of astronomical observation. Its contributions woven into nearly every major cosmological discovery of the late 20th and early 21st centuries. Yet Hubble's capabilities had limits. Infrared radiation from ancient distant galaxies was stretched to such long wavelengths by cosmic expansion that Hubble, optimized for visible and ultraviolet light, could not detect it. This limitation was overcome by the Spitzer Space Telescope, which specialized in infrared observations, revealing dust-shrouded galaxies and the faintest signals from the universe's earliest epochs. The James Webb Space Telescope, launched in December 2021, represented a quantum leap in capability. With a mirror 3 times larger than Hubble's and optimized for infrared wavelengths, Webb could observe objects far more distant and ancient than any previous instrument. Its observations confirmed and extended the shocking findings about early massive galaxies. Webb detected the most distant galaxies known, existing merely a few 100 million years after the Big Bang, allowing astronomers to probe the epoch of galaxy formation more directly than ever before. The Planck satellite, operated by the European Space Agency from 2009 to 2013, mapped the cosmic microwave background with unprecedented precision. Its observations revealed the imprints of primordial fluctuations with exquisite detail, allowing cosmologists to determine the age of the universe, the amount of ordinary and dark matter it contained, and the rate of cosmic expansion. Planck's data provided the foundation for modern cosmological models, constraining theories of galaxy formation and cosmic evolution. Ground-based telescopes complemented space-based observations. The Keck Observatory in Hawaii, with its 10-meter mirrors, could perform spectroscopy of extremely distant galaxies, measuring their redshifts and chemical compositions. The Very Large Telescope in Chile combined multiple telescope mirrors to achieve unprecedented angular resolution, allowing observation of fine detail in distant galaxies. Radio telescopes, such as the Very Large Array in New Mexico, detected emissions from hydrogen and other elements, tracing the interstellar medium and revealing the structure of galaxies in 3 dimensions. The Sloan Digital Sky Survey represented one of the most ambitious systematic surveys in astronomical history. Over more than 2 decades, it cataloged millions of galaxies, measuring their positions, colors, and redshifts. This vast database allowed astronomers to trace the large-scale structure of the universe, revealing the cosmic web of filaments and voids in unprecedented detail. Analysis of SDSS data provided insights into how galaxies were distributed, how they clustered together, and how that clustering evolved over cosmic time. Particle physics experiments contributed to understanding galaxy formation through a different avenue. The Large Hadron Collider at CERN recreated conditions approaching those of the early universe, testing theories of particle physics that governed cosmic evolution. While LHC experiments did not directly study galaxies, they tested the fundamental physics underlying galaxy formation. The non-discovery of certain exotic particles constrained theories of dark matter and modified physics at extreme energies, indirectly shaping understanding of the early universe. Computer simulations provided another crucial tool. Supercomputers at institutions worldwide ran sophisticated hydrodynamic simulations, incorporating gravity, gas dynamics, radiative processes, and feedback mechanisms. These simulations attempted to replicate galaxy formation from first principles, beginning with the density fluctuations imprinted in the cosmic microwave background and evolving forward through billions of years of cosmic time. Modern simulations, such as Illustris, Eagle, and Magneticum, achieved remarkable success in reproducing observed galaxy populations, though they still contained uncertainties and limitations. Gravitational wave detectors added a novel dimension to observational capability. Events like the merger of 2 neutron stars could be detected through ripples in spacetime itself, providing information about extreme physics and heavy element synthesis. While current detectors were not yet sensitive enough to study galaxy-scale gravitational wave sources, future instruments promise to open entirely new windows onto cosmic catastrophes and the violent processes driving galaxy evolution. The Lyman alpha forest, an absorption feature visible in the spectra of distant quasars, served as a diagnostic tool for tracing the distribution of hydrogen in the intergalactic medium. By studying how many absorption features appeared in quasar spectra, astronomers could map the epoch of reionization, determining when the universe's neutral hydrogen transformed into ionized plasma. Baryon acoustic oscillations, measured through large surveys like Baryon Oscillation Spectroscopic Survey, BOSS, and the forthcoming Dark Energy Spectroscopic Instrument, DEI, provided standard ruler measurements of cosmic distances. In the early universe, acoustic waves in the plasma of charged particles created a characteristic scale. This scale, preserved in the spatial distribution of galaxies today, provided an independent measure of cosmic expansion history, complementing supernovae and other distance indicators. These tools, telescopes spanning from radio to X-ray wavelengths, satellites free from atmospheric distortion, particle accelerators probing fundamental physics, supercomputer simulations of cosmic evolution, and survey instruments mapping millions of galaxies formed an intricate web of observational capability. Each tool provided a different perspective on the cosmic mystery, revealing different aspects of galaxy formation and evolution. Together, they drove the ongoing quest to understand how galaxies are born, from the quantum fluctuations at creation to the mature structures we observe today. The scientific investigation of galaxy formation, rigorous and empirical though it is, leads ultimately to a threshold where physics meets philosophy, where measurement yields to meditation, where the observable universe whispers of deeper questions about meaning, existence, and the human place in creation. We stand, at this moment in cosmic history, as conscious observers, beings capable of understanding the very universe that created us. This is itself a profound mystery. Matter organized into complex patterns has somehow achieved the capacity to contemplate its own origins. The atoms that form our bodies were forged in stellar furnaces billions of years ago. The carbon in our DNA, the iron in our blood, the calcium in our bones, all were synthesized in the cores of ancient stars and dispersed into space through stellar explosions. We are, quite literally, made of stardust, assembled by the cosmos into a form capable of observing itself. When we contemplate galaxy formation, we are not contemplating something distant and separate from ourselves. We are contemplating the process that made our existence possible. The Milky Way, our home galaxy, did not exist forever. It formed billions of years ago from the merger of smaller protogalactic systems, assembled under gravity's patient hand from gas seeded with the primordial fluctuations established moments after creation. The Sun, around which we orbit, is a late-generation star, formed from material enriched by billions of years of stellar nucleosynthesis. Without the process of galaxy formation and stellar evolution, the Sun would not exist. Without the Sun, Earth would not have formed. Without Earth, humanity would not have arisen. The mystery of galaxy formation is, in some sense, the mystery of ourselves, where we come from, why we exist, and what role we play in a cosmos vastly larger than individual consciousness can easily fathom. Contemplating this mystery generates profound emotional responses. There is awe, the recognition of cosmic immensity, the staggering numbers of galaxies and stars and planets, the vast distances and time spans involved in cosmic history. There is humility, the realization that our species is microscopically small, inhabiting a single planet orbiting an ordinary star in one galaxy among hundreds of billions. There is wonder, the delight in mysteries yet unsolved, in questions yet unanswered, in an infinite frontier of discovery. Yet there is also disquiet and existential questioning. The universe revealed by science is not the universe humanity long imagined. It is not designed for human comfort or comprehension. Most of it is inaccessible and alien, the crushing densities of black holes, the roiling chaos of stellar cores, the vast voids between galaxies stretching for billions of light years with nothing but vacuum and darkness. The universe appears indifferent to human concerns, governed by forces that predate and will outlast our species. The discovery of dark matter and dark energy adds additional layers of philosophical unsettling. The universe we perceive with our senses, stars, planets, galaxies, all visible light and matter comprises less than 5% of cosmic content. The rest is darkness, darkness we cannot see, cannot touch, cannot directly perceive. Our entire visible universe, the entire domain of human experience and observation, is embedded in and dependent upon invisible forces, of which we understand almost nothing. It is as if we live on the surface of the ocean, observing only the small portion visible above water, unaware that beneath us lies an abyss of vastness and strangeness. The philosophical implications extend further. If galaxy formation proceeded through such a precise interplay of countless physical processes, if the outcome depended sensitively on the values of physical constants, the properties of dark matter, the magnitude of cosmic expansion, then the universe appears finely tuned. Small variations in physical laws could have resulted in universes where galaxies never formed, where stars never ignited, where life never emerged. This observation has given rise to the anthropic principle. We can observe a universe with these particular properties because a universe with the capacity to generate observers necessarily possesses those properties. But does this imply that fine-tuning is anthropically inevitable? Or does it suggest something more profound about the nature of reality? Some physicists and philosophers have speculated about multiverses, infinite collections of universes, each with its own physical constants and laws. In such a framework, universes like ours, capable of generating observers, are rare but inevitable. Yet such speculations venture into territories where empirical science can no longer observe or test. The multiverse remains a mathematical construct, consistent with current theories, but potentially unobservable and unfalsifiable. The ongoing nature of scientific investigation itself carries philosophical weight. The quest to understand galaxy formation is not approaching completion. Rather, each discovery opens new mysteries. Each answer spawns new questions. Scientists have moved from ignorance to partial understanding, but complete understanding appears to recede infinitely into the distance. This is not a failing of science, but a reflection of the profound inexhaustibility of reality. The universe is, in some sense, inexhaustibly meaningful. There is always more to understand, always deeper layers to explore. The emotional experience of contemplating galaxy formation is thus complex and multifaceted. There is the intellectual satisfaction of understanding the joy of grasping pieces of the cosmic puzzle, of explaining natural phenomena through laws of physics. There is the emotional awe at beauty and vastness, the spiral arms of a galaxy photographed by Hubble, the infant universe as revealed in microwave background maps, the jets of radiation from active galactic nuclei extending across millions of light years. There is the existential vertigo of confronting cosmic insignificance, the awareness that in the scheme of the universe, human concerns appear almost infinitesimal. Yet there is also profound meaning that emerges from this confrontation with vastness. The fact that we can understand that our brains, made from common atoms and operating according to physical laws, can grasp the principles governing galaxy formation is itself remarkable. We are not separate from the cosmos, observing it from outside. We are part of it, intimately woven into its history and its future. The universe, in producing conscious observers, has achieved a form of self-knowledge. Through our investigations, the cosmos comes to know itself. The investigation of galaxy formation also connects to questions of cosmic destiny. What is the ultimate fate of galaxies? As the universe continues to expand under the influence of dark energy, galaxies will gradually drift apart. Stars will exhaust their fuel and fade into darkness. Black holes will grow ever larger, consuming remaining matter and eventually evaporating through Hawking radiation. Trillions of years hence, the universe will enter an era of extreme cold and darkness, when virtually all structure will have decayed into radiation and fundamental particles. Yet this far future fate casts no shadow on the present. Galaxies continue to form, stars continue to ignite, and the universe continues its grand tapestry of creation and evolution. The meaning of galaxy formation, then, extends beyond scientific comprehension. It touches profound questions about existence. Why is there something rather than nothing? What laws govern reality? What is humanity's role in the cosmic scheme? These are not questions that science alone can answer. They require philosophy, poetry, and imagination, working in concert with empirical investigation. As we drift through the cosmos, observing the ancient light of distant galaxies, contemplating the quantum fluctuations that seeded all structure, we participate in a profound human endeavor, the quest to understand our origins and our place in creation. The mystery of how galaxies are born is not a puzzle to be completely solved and set aside, but a perpetual invitation to deeper contemplation. In pondering this mystery, we contemplate ourselves, our origins, and the infinite potential that lies within the cosmic void. The galaxies continue their eternal dance, drifting through expanding space-time, each one an island of light and complexity in the infinite darkness. And we, conscious beings assembled from stellar material, remain forever fascinated by the questions. Where do they come from? How were they born? And what does their existence mean for us? These questions have no final answer. They are invitations to perpetual wonder, perpetual investigation, perpetual growth. In that spirit, we continue to observe, to question, and to dream of understanding the profound mystery of cosmic creation. Subscribe to our channel to join us on future journeys into the depths of cosmic mystery. Each episode explores a new question. Each answer opens new doors. The universe is vast, ancient, and endlessly fascinating. Drift with us. Asterisk.